in log functions, in these notes specifically, there's a lot of like basics. One, you have been exposed to logs, so it's a little bit of a refresher on evaluating logs. But then when you get into graphing logs, evaluating using a calculator, and then LNs, which are natural logs. So we start with what is a log, okay? So that log notation would be y equals log with the little a, and then the x next to it. And that's read as log base a of x. So y equals log base is the bottom little number, subscript, and then the x next to it. And the first thing we're going to do is review how to convert from log to exponential, and then back from exponential to log. If you had Miss Corey, she teaches you Bay. How many of you had Miss Corey last year? You know what I'm talking about? Yeah, okay, so the base, the a, and then the exponent. That's how she teaches it, but I'll show you both ways. Basically, what you do is the little base from the bottom comes over and picks up the one that's by itself, and then it drops off, leaving whatever it was next to. So it would be a to the y equals x. She would do b for base, the a over here, and the e becomes, right? That's what she does? Yeah, and then the e goes by itself. So it doesn't matter how you remember it as long as you remember it. One of the tricks I usually teach is that no two things stay together. So if they're together on one side when they're a log, they are not together anymore when it's exponential, and vice versa. If I have an exponential function, then the base of the exponential function becomes the base on the log, and then it drops off. That y is going to be by itself. It gets the x equals y. So again, no two pairs are ever kept together when you go from one expression to the other. So the very foundation is converting one from the other, okay? This is called a log function because we now have f of x in there, which means these would still pass your one-to-one. Your vertical line test because they're still functions. All right, so again, log form, y equals log base b of x. Exponential form, b to the y equals x. So in numeric form, 2 to the third would equal 8. So log base 2 of 8 would equal 3. You got to be able to get from one to the other. And then eventually we'll simplify it. So if you just had something like this, we would actually take it a step further and simplify it. All right, so the first one is converting. Write the equation in the equivalent exponential form. So if I have 4 equals log base 2 of x, then the 2 comes over and picks up the 4, 2 to the 4th, and it drops off and leaves the x by itself. And here, 3 to the x drops off, so 3 to the x equals 9. Right now, we're just converting. Obviously, at some point, we will solve these, but for right now, we're just converting. Example 2 is the other way around. Write the equation in its equivalent log form. So the base on the exponential function becomes the base on the log. The 16 comes to the side with the b, and the 4 gets bumped to the other side. Log base 5 of x would equal 2 here. And sometimes people are better at the log to exponential. So like if you do go to exponential, you can always check it. Does the b pick up the 4? Yes, and then drop off, leave the 16, and it matches your question. Raise your hand if you remember this from last year, at least slightly. Okay, good. Questions so far? Okay, now we're going to use these to evaluate the log function. So it says evaluate the function at the indicated value of x without using a calculator. So this is just saying f of x would equal log base 4 of 64. I know I'm a nerd, but the fun part about logs, if there is a fun part, is that these can be mental math. So you can go the long way with this. I could set it equal to y. I can convert it to exponential. I can do my change of base like we did before. I'll show you the long way in a little bit. Or you can get so good at logs that you can understand that really what this is saying is what power do I raise 4 to get the 64? And 4 to what power is 64? 3. So f of x would equal 3. That's why these can be fast. Like if you're really comfortable with logs, these can be quick. The long way around is I would rewrite that as y equals log base 4 of 64. I would convert it to exponential, so 4 to the y equals 64. And then I could change the base. 4 to the y would equal 4 to the third. And then once the bases are the same, I can set the exponents equal to each other. My goal for you is to be able to do it on the left. Do it with mental math because it will make it fast. You can always check it the other way, but you want to be able to do these because you're pretty comfortable with them. Okay, go to B. So log base 36 of 1/6. So two things are happening here. One is the 36 is going to something in the bottom. How would something move from the base or from the numerator to the denominator? Negative exponent. And then how would I go from 36 to 6? Other way around, right? If it was 6 to 36, I'd square it. But if I have to go from 36 to 6, it's a square root, right? What's a square root look like as an exponent? It's a fraction, specifically what? 1/2. So this is negative 1/2. So if we're square rooting, then the exponent is a half. If we're moving our number to the bottom, then it's a negative. Again, long way around is always an option. I would say y equals log base 36 of 1/6. 36 would pick up the y. And then I can either change both sides or I could just change one side. If I want to bring the 6 to the top, it'd be 6 to the negative 1. And if I wanted to rewrite 36, it would be 6 squared. And then the y is there. So I'd multiply those together. I'd get 2y equals negative 1 and y equals negative 1/2. But better than the long way is understanding the mental math part of it. If I need to move it from top to bottom or bottom to top, it's a negative exponent. If I'm square rooting, it's a half. All right, now we're going to use the calculators. So on the left-hand side is if you have like a graphing calculator or a calculator that stores. The right-hand side is if you actually type something, which is our graphing calculator. So if we type something in and it stores the word, you're going to follow the right-hand side. The left-hand side is if you have a scientific that doesn't store, so like the calculator on your phone, if you turn it sideways, or the old school scientific ones that if you just hit the button, the word log doesn't appear. So we're going to focus on the right-hand side because this is what ours does. So first of all, log by itself means log base 10. If you just see log, it means log base 10. So when you have a log button on your calculator, it is LOG. It is above the LN button that we used last week. Okay? That means log base 10. So if I want to find log of 1,000, like if this is my question, then what it's really saying is log base 10 of 1,000. So I literally just do log 1,000, enter. You should get 3 because 10 to the third is 1,000. So I want you to be practicing these. Make sure you're doing it with your calculator. If I did log of 5/2, I'm going to do log 5 divided by 2. Make sure it's still in the parentheses. Don't close your parentheses. And then hit enter. And you should get 0.39794. If I want to do log of 5 over log of 2, I have to do log 5, close the parentheses, divided by log 2. And you should get 2.32198 and so on and so forth. Everybody's getting this? Yes? And if I do log of negative 3, your calculator should give you an error. It says non-real answers because there is nothing I can raise 10 to make it a negative number in general, let alone negative 3. So anytime you have a log, no matter what this base is, this base could be anything here. If this is a negative number, your answer is, it's not possible, okay? So it'd be no solution or no real number. I think on website, D&E does not exist, okay? Questions so far? So with that log button, it can only be log base 10. We're going to teach you how to do it without, if it's log base anything else. I'm going to teach you something else. But if that says log, then it's log base 10. All right, so it says use a calculator to evaluate the function at the indicated value of x. This is negative 3 log, and then log base 10 doesn't need to be there. It could just be log of 2.7. And our calculators can handle that whole thing. -3 log 2.7. -1.294. It didn't say what to round it to, but just do 3. Still with me? Good? Okay. Now we've got some mental properties of logs. So these are things that you want to be able to recognize without having to do work. The first is log base A of 1 is going to be 0. Anything, could be any base here. If this number is 1, then my answer is always 0. It could be log 1, log base 5, 1, log base 25, 1. It doesn't matter what it is. That answer is going to be 0 because in order for something to be 1 as its answer, it has to get raised to the even power. So A to the 0 would equal 1. If the base and the number next to it are the same, then my answer is going to be 1 because anything raised to the first power is going to be 1. This should be here. Ignore that. Because A to the first is 1. So if this said log 5 of 5, so log base 5 of 5, that answer is 1 because they're the same. So if the base on the log and the number next to it are the same, it's 1. If you're raising, like if the base, you're doing log base something of a number raised to a power and the base on the log and the base on the exponential function are the same, then you can eliminate them and just keep the exponent. So that would look like log base 5 of 5 squared. When the base here is the same as the base here, you literally ignore them and grab the exponent as the answer. And the reverse is true here. If I have an exponential function, which is what this is, being raised to a power that has a log with the same base as my exponential function, so the A here and the A here are the same, then I cancel out everything and keep what's next to the log. So something like that would look like 5 log base 5 of 2. Because this base and this base are the same, we literally ignore them and we grab what's next to the log in the exponent. And then the last is your one-to-one property with logs. Just like we did with exponential functions, if the exponential on either side of an equation have the same base, we ignored the base and set the exponents equal to each other. If the log and the base on the log are the same, then we ignore them and we set what's next to them equal to each other. So if I had log base 2 of x equals log base 2 of 10, then x is 10. You ignore the log and the base. They have to be the same, but you can ignore them and then you set what's next to them equal to each other. We still good? Yes? Questions? Okay. So now try to do this without even converting it into an exponential function. Kind of just look at the left-hand side of this and see if you could simplify it. Log base 3 of 81. What's that answer? 4, because 3 to the 4th is 81, right? So x is 4. Go to B, log base 5 of 1. What's that answer? 0, because 5 to the 0 equals 1. Still good? Yeah? Okay. See if you can work through these. Try them. All right, what do we get for A? 15. The 3 and the log base 3 cancel out. What did you get for B? 3. The log base 2 and the 2 cancel out. What did you get for C? 1. Because if the base and the number next are the same, it's 1, right? And what did you get for D? -1. Good. We want the value to stay the same, but we want it to move. Raise your hand if you got all 4 right. Good. Okay. If you can understand logs and you can do them quick, it will make everything else so much easier after this. Okay. All right. So next up is your graphs. We graphed exponential functions last week. Okay. We're going to graph logs this week. And a log and an exponential are inverses of each other. So everything that was true about the x on the exponential becomes true about the y on the log. Everything that was true about the y becomes true about the x. So we flip-flop it, which means anything we knew about domain on exponential, we now know about range on log. And anything we knew about range on exponential, we now know about, what did I say? range. We now know about domain on logs, okay? How we graph it, we even flip. So there's a couple different ways to graph it. You can graph a parent function and you can shift it, which is easy when it's simple, but it gets complicated when you start to add things or reflect it. So I teach a different way to graph it, okay? If you want to graph the parent and shift it, go for it. But I will tell you, I would recommend doing it the way I'm going to teach you. So first of all, the blue one is my exponential function from last week, okay? It had a horizontal asymptote, and it increases and moves to the left, going away from that horizontal, right? Now, this is a log function. It almost looks like a square root function, except it doesn't end. And it has a vertical asymptote. So now we're going to do everything based on that. On the bottom in the box, it says the x-intercept is 1, and there's no y-intercept unless there's a shift. So this is based on the parent function. If you remember from exponential, the y-intercept was 1, and there was no x, so we switched it. The y-axis, or x equals 0, is a vertical asymptote. If b is greater than 1, the function is increasing, and if b is between 0 and 1, the function is decreasing. The graph, just like exponential, is smooth and continuous, no sharp corners or gaps. The domain of log functions are now restricted. So in an exponential function, our domain was all real numbers. Now the range is all real numbers. And the domain is all the positive real numbers, or 0 to infinity, and shifts with a horizontal shift. We're going to find the vertical asymptote by setting the parentheses equal to 0. And we're going to find the x-intercept by plugging 0 in for y. So the biggest difference is that we are going to actually plug in for y this time. We're going to convert it to exponential. The exponent will now have the y in it, and then we're going to plug in for the y instead of the x. All right, transformations work exactly the same. I would say you want to use this to kind of know what your graph is going to look like, but we're going to plot the points to be exact. If you add or subtract after the function, it shifts it up or down, just like normal. If you add or subtract inside the function, the plus shifts it left, the minus shifts it right. This is what changes your vertical asymptote. So this is what we have to pay attention to for the vertical asymptote. If there's a negative on the front, it flips it over the x-axis. If there's a negative inside, it flips it over the y-axis. If there's a scalar multiple on the front, bigger than 1, it stretches it vertically. In between 0 and 1, vertically shrinks it or compresses it. And if the scalar multiple is inside the parentheses and it's bigger than 1, it's a horizontal shrink. And if it's in between 0 and 1, it's a horizontal stretch. Again, the thing you have to pay attention to the most is your horizontal translation, because that impacts where your vertical asymptote goes. And then if you plug those same 3 numbers in that we've been plugging in, but we're going to plug in for the y, it will take care of the rest of this. All right, so we're going to ignore the 3 of x. We'll talk about it later. What we're going to go right to is the log base 3 of x. So first of all, is there a horizontal shift? No, which means my vertical asymptote is at x equals 0. Whatever's here, I would set equal to 0 to find that. Which means I have a vertical asymptote through 0. Then I'm going to change my g of x to a y. And I'm going to convert this to exponential. So the 3 picks up the y, drops off, and leaves the x. And then I'm going to plug in, but this time I'm going to plug in for my y value instead of my x. So I get 3 to the negative 1, which is 1/3. I get 3 to the 0, which is 1. And I get 3 to the first, which is 3. And then the biggest mistake people make is doing negative 1, 1/3. They literally reverse it in their head. Be really careful. That 1/3 is my x. So 1/3 negative 1 is here. 1, 0 is here. 3, 1 is here. And then I bend that curve to go along the the vertical asymptote, which is the y-axis. What's the domain of this function? 0 to infinity. So it can't touch that 0. It gets a parentheses. What's the range? All real numbers, negative infinity to positive infinity. The vertical asymptote we found up here, and my my x-intercept, x-intercept. Still the middle of my t-chart if you've done it correctly, 1, 0. Now, if you had plot both of these on the same axis, this would have been here, here, and here. It would have looked like this, and there would have been a horizontal asymptote, like if I had plotted x to the third. And what happens there is these are inverses of each other. So if I had taken all of those x and y coordinates and flipped them, switched the x and the y, you end up with your log function. But when I give you a test question, it's going to ask you to go straight to log. So you don't need to go from exponential to log, which is why I taught you that way. All right, this one says use transformations to graph it. We're going to graph it the original way, but describe the transformations before you do it. What's the negative on the front do? Flips it over what? X-axis. What's the minus 1 inside? Right 1. So where's my vertical asymptote this time? Good, set it equal to 0, so x equals 1. Now my vertical asymptote shifted to the right, it's at 1. Now I'm still going to use a t-chart, so I'm going to change that to y equals negative log base 3 x minus 1. And before I can convert it to exponential, I have to get rid of anything that's on the front of this log. So if there's a negative there, I'm going to multiply by negative 1 to get rid of it. If there was a scalar there, if it said 2, I would divide both sides by 2. So you have to get rid of anything that's on the outside of that log first. So this becomes negative y equals log base 3 of x minus 1. Then the 3 picks up a negative y, drops off leaving x minus 1. And then I'm going to solve for x, so I'm going to add the 1. And I get 3 to the negative y plus 1 equals x. And I'm going to plug in for y. So 3 to the negative 1 plus 1 is 3 to the first plus 1, or 4. 3 to the 0, negative 0 plus 1 is 1 plus 1, which is 2. And 3 to the negative 1 plus 1 is 1/3 plus 1, or 1 1/3. So then I go 4, negative 1, 2, 0, 1 1/3, 1. And we took that arc shape, right, and we flipped it upside down because it flipped over the x-axis, which means it's going to hug it this way, and the arrow is going to point away from it that way. What's the domain on this guy? 1 to infinity. What's the range? All real numbers. We said our vertical asymptote was at x equals 1, and our x-intercept would be 2, 0. Questions so far? Okay, I'm going to hold this one off, okay? It would be the same process, right? 4 would pick up the y, and then you'd add 5 to it. So it would be 4 to the y plus 5. And then we would plug in for negative 1, 0, and 1. Do you know where to go from there? Like, am I okay to skip this extra example? Okay, good. Because I want to get to ln's. So you remember E was called the natural base. Well, log base E is called the natural log. So log by itself is log base 10, and log base E is the same thing as ln. ln is called the natural log. It has all the same characteristics of log. It's actually very, very similar to log base 3 because E is like 2.7. So it has almost all the same characteristics as log base 3. It would just be a little bit different on the plotting of the points, but the overall characteristics are the same. So when you use ln, which is in your calculator, right? Last week we used the E and we did second ln. This time you're going to actually use the ln button. It says use the calculator to evaluate the function at the indicated value of x. Round to 3 decimal places. So this is 2 ln 12.5. You don't need to change that to log base E. You just do 2 ln 12.5. And I get 5.051. Easy stuff, right? Now here's some properties. These you don't need a calculator for. It says use the properties of natural logs to rewrite the expression. So if I look at A, that says -5 of ln of E. Okay? The long way is let's replace ln with what it equals. What is the ln? Log base E, and this is log base E of E. What happens when you have log base E of E? Like what happens when the base and the thing next to it are the same? This is just 1. So I'd get -5 times 1, which is -5. Now the shortcut is ln of E equals 1. It really equals whatever the exponent on that E is, so that that exponent changes, then it's just the exponent, but E is raised to the first if it's by itself. So that answer is 1. So then I could have just done -5 times 1, which is -5. B is the reverse. This says E ln of 7. So E to the log base E of 7 is the same thing, right? E cancels with the base on the log, and this is just 7. Questions on those? All right, last thing we're going to do is graph an ln. So this you would need a calculator for, okay? Because it's going to be an E as your base. So it's going to say find the domain, x-intercept, vertical asymptote, and the log function, and then sketch the graph. First of all, the domain and the vertical asymptote we should be able to do without, right? Because where's the vertical asymptote come from? Set this equal to 0, right? My horizontal shift, which tells me my vertical asymptote is at x equals 3. So I'm going to have a vertical asymptote at 3. And then this has no reflection, which means it's going to be an arc that points to the right, which tells me that my domain is 3 to positive infinity. Those things I don't even need the calculator for. Now, if it wants you to fill out a t-chart, you're going to fill out a t-chart. And if it wants you to keep it like round, whatever it will say. But I'm going to say y equals changing ln to log base E of x minus 3. And then E is going to pick up the y, drops off, and leaves x minus 3. And I get E to the y plus 3 equals x. And then I'm going to plug in for the x. So now it's E to the -1 plus 3, E to the 0 plus 3, and E to the first plus 3. Now, you could really do 2 of these without a calculator, but specifically that middle one, what is E to the 0? This would be 1 plus 3, which is 4. So that you could do without a calculator. What is E to the first? What do we approximate E to be? 2.7. So this would be 2.7 plus 3. That could also be done without a calculator. The only one I really need it for is E to the -1. So second ln, -1. So it's E to the -1 plus 3. And that's 3.36. So we're going to round it to 3.4. So I get 3.4, -1, 40, 5.71. And I know to hug the vertical asymptote and point it away. I already did the domain. I did the vertical asymptote. The x-intercept is 4, 0. So I would say most likely your quiz will be non-calc. You'll do just the non-calc stuff. So if you're graphing, it will just be the logs. By the time test rolls around, you'll get both calc and non-calc. And on that part, you could see something like this where you'd have to use your calculator. Questions on anything we did today? Good job. It was a lot.